If you don't have a table of Kas or pKas, then you can compare the strength of two different acids. You can compare how likely two different H's are to pop off of a molecule qualitatively by looking at 4 different factors. And these are very much a rule of thumb. There are plenty of exceptions to these, but they're a general guide so that you get a qualitative sense of which hydrogens are more acidic in a molecule, which hydrogens are most likely to pop off of a molecule. So the 4 factors can be summarized by a little mnemonic device called ARIO. So let's go through these one at a time. This first exercise, exercise 313, is just going to be going over the first factor, and that is which atom the hydrogen is on. So the trend that we're going to see is that if 2 atoms are in a column, so a group, a hydrogen on an atom further down is more acidic. And in a row, a hydrogen on an atom further to the right is more acidic. All right, so that's our first general rule. Now let's go through why that would be the case. As you go down on the periodic table, atoms get bigger. And so if you were to look at a periodic table with the different sizes of different atoms, you'll see that in general, as you go down, the atoms become much larger. So if you take, for example, this column over here, you'll see that as you go down, the atoms get larger. And if you do that with any column on the periodic table, you'll see that they get significantly larger as you go down. Because you have a new shell, right? Electrons wrap around the nucleus of an atom in layers, sort of like layers in an onion. And so as you go down, the number of layers gets larger. Every column in the periodic table represents a new one of these layers. So you go down to the second column and you get 2 layers, and as you go further down, you get even more layers. And so the atoms get bigger. So as you go down on the periodic table, atoms get bigger, and the difference that makes is if you're trying to think about an acid, something like HF and HI, which one of those would be more acidic? Well, imagine that the H really does leave, the H plus really does leave. That goes away. Oops, actually I can do this. It leaves the molecule. Doesn't take electrons with it, so it has a plus charge. And the electrons in the bond then would go onto that other atom that stayed behind. Now, this fluorine had 3 other lone pairs to begin with, but this is the lone pair that was in the bond. And so that has a negative charge. And so a similar thing could happen to this HI molecule. The hydrogen can leave. If it's acting as an acid, then that's what it does. It wouldn't take any electrons with it, so it would gain a positive charge, and the electrons in this bond right here, those would become a lone pair just on the iodine, so now the iodine has a full negative charge. But notice, if you try to fit a full negative charge in a fluorine atom, there isn't a lot of space. Whereas if you try to fit the same amount of charge in an iodine atom, there's so much space. The charge gets spread thinner, it's more diluted in an iodine atom. And so the larger atoms get, the more space they have that they can use to stabilize a negative charge. And if the atom becomes more stable, then the hydrogen can get away. If the atom is less stable, when the hydrogen is trying to leave, the negative charge attracts it and it just snaps right back. And the hydrogen ends up not getting away, and so the molecule doesn't really behave like an acid as much. So, as you go down in the periodic table, the atoms get bigger, and as they get bigger, they get better able to stabilize. They get better able to stabilize the negative charge that they have when hydrogen leaves. And so as you go down in a column, the hydrogens are more likely to leave because what the atoms they leave behind will be larger and better able to stabilize the negative charge. So the hydrogen will leave more often. So that's the first trend. Now, if you compare what happens when you go down on the periodic table to, say, what happens when you go from left to right, the size does get bigger as you go to the left, but it's not as dramatic. You compare this far left column, where the atoms get really big as you go down. Compare that to this left-right column. I'm sorry, this left-right row, this row. The atoms don't change as much in size when you go from left to right, because as you go up and down, you're adding a new layer into the atoms. But as you go from left and right, you're in the same layer. The atoms are just flying in more energetic ways. So when you go from left to right, it's a different trend that stabilizes a negative charge. And that trend is electronegativity. Imagine, instead of iodine and fluorine like we had last time, imagine that you have fluorine and hydrogen. So if this hydrogen has a negative charge around it, if it gets another electron and it has a negative charge, it only has one proton in its nucleus to help stabilize the negative charge. Fluorine, though, has many more protons in its nucleus. It has 9. And so it is more electronegative. All that positive charge is going to attract those valence electrons. It'll bring them closer to the nucleus. And when the valence electrons, that negative charge gets closer to the nucleus, it gets stabilized more. So as you go to the right on the periodic table, elements become more electronegative, and what that means is they take the negative charge that's left behind and they hold it close to the positive charge in the nucleus to help stabilize it. So say you have H2, hydrogen gas, and compare that with HF. If this H2 were to act like an acid, one of the hydrogens would have to leave and not take the electrons with it. So it would be H+. And that means you would just have a negative charge on hydrogen. Now already that's very unstable because it's a small atom. But it's also unstable because there's not a lot of positive charge that the nucleus can use to help stabilize the negative charge. If you do the same thing with fluorine, if the hydrogen gets up and leaves, and the lone pair that was in the bond becomes a lone pair on the fluorine, and that would have had 3 other lone pairs, so the full charge is negative. The fluorine can stabilize that negative charge because it can bring it closer to the nucleus through the power of its electronegativity and stabilize it better with its positive charges. So that happens as you go to the right, because as you go to the right on the periodic table, the amount of positive charge that you have in the nucleus gets bigger, and so the electronegativity gets bigger. So those are the explanations for this trend. But all we have to know is that if you're in a column, the hydrogen that's on an atom further down, a bigger atom, will be more acidic, because the atom it leaves behind will be able to use its size to stabilize the negative charge. And if two acids are in a share, if the hydrogens in 2 acids are in a row, the atom they're connected to are in the same row, then the one further to the right is more acidic because it's more electronegative and it will be able to stabilize the charge that's left behind better. So let's see how that would apply to exercises like this. So you'd look at the 2 hydrogens. The blue one is on an oxygen. The red one is on a carbon. Those are different atoms. So if we look at a periodic table, you would see that those 2 elements are in the same row of the periodic table. So So we have oxygen here, carbon here. Those are in the same row, and as you go to the right, the atom becomes more electronegative and better able to stabilize a negative charge left behind when one of the hydrogens leaves. So as you go to the right, the hydrogen on an atom further to the right is more acidic. That hydrogen would be the more acidic one. And to help see why, you can draw the two possible molecules you would get. If this blue hydrogen leaves, then you are left with this molecule. And if the red hydrogen leaves, you're left with this molecule. And so, which hydrogen is more likely to leave? The one that leaves a more stable molecule behind. And that is this molecule on the right. That's more stable because the negative charge here is on an atom that's able to pull the negative charge closer to the positive charge in its nucleus, because it's more electronegative. And so it stabilizes it. All right, we can play a similar game with this next one. Let's look at the atoms that each of the hydrogens is on. The blue one is on a nitrogen, the red one is on a carbon, so those are different atoms. So we'd go over the periodic table and we'd notice that we have nitrogen and carbon, they're in the same row. The rule we saw was that the hydrogen on an atom further to the right is more acidic. So this hydrogen on a nitrogen, which is further to the right, is more acidic. That is the hydrogen that's likely to come off of this molecule, the blue one. And to see why, you could draw the two possibilities. If the red molecule comes off, the red hydrogen comes off, you would be left with this. And if the blue hydrogen comes off, you would be left with this. So here, which hydrogen is more likely to come off? The one that leaves the more stable atom or molecule behind, and that is this blue one. That's because nitrogen is more electronegative than carbon is. So this negative charge here is pulled closer to the nucleus of nitrogen, a nucleus that is able to put its positive charge and help to use that positive charge to stabilize the negative charge. Whereas carbon holds the electrons further away from its nucleus because it's not as electronegative, and so it's not able to stabilize the negative charge as much. Okay. If we look at C, we will notice that we have two atoms here. We've got a blue one and a red one. The blue hydrogen is on an oxygen. The red hydrogen is on a sulfur. So if we look at the periodic table for those two, we'll see oxygen and sulfur, those are in the same column. And our rule was that in a column, hydrogen on an atom further down is more acidic. So sulfur is further down, so the red hydrogen here will be more acidic. That's on an atom that's further down. And to see why, you can draw the two possible molecules. If the red hydrogen comes off, you'd be left with this. If the blue hydrogen comes off, you're left with this. So which of those is more stable? The molecule on the left is more stable because the negative charge, that's the thing that's making these unstable. The negative charge in the left is on a bigger atom. Sulfur is bigger than oxygen would be. So you can take the negative charge and spread it out over a larger space so that at any individual space it's smaller. Whereas with oxygen, the charge would be stuffed in a tiny space, and that would be very unstable. It would be repelling itself very strongly. Okay. Last for this one is D. So here we have two atoms. Oops. So for D we have two atoms, two different atoms with a hydrogen on it. We have a nitrogen and an oxygen. So we'd go to the periodic table, we'd look for those. Nitrogen and oxygen are in the same row. Our rule was, if two atoms are in the same row, the hydrogen on the atom further to the right is more acidic. So which is further to the right? Oxygen. So the red hydrogen will be more acidic. And the reason for that, we can see if we draw the two molecules. If the red hydrogen comes off, we'd be left with this. And if the blue hydrogen comes off, we would be left with this molecule. So which is more stable? It's the molecule on the left. What's making these molecules unstable is the negative charge. And for the molecule on the left, the negative charge is being pulled really close to the nucleus of that oxygen atom, because oxygen is so electronegative. It pulls the electrons toward the nucleus, pulls the negative charge toward the nucleus, where there's a whole bunch of positive charge. And so it helps to cancel out that negative charge and stabilize it. So that's how you can use the atom that a hydrogen is on as the first factor you want to consider to help to compare two different acids, the strength of two different acids.